Hello friends, what's up? Welcome back to the channel. And in our previous video we learnt about speed and velocity. So today we learn about the rate at which the speed or the velocity of an object changes, and this rate of change of velocity of an object is called as acceleration. Now acceleration, like velocity, is a vector quantity because it is defined as the rate of change of velocity, and it's a vector quantity. That means it has both magnitude as well as direction, and the SI unit of acceleration is meter per second square. So mathematically you can write acceleration as rate of change of velocity, and the unit of this rate of change is in meter per second, and you divide this by second. So that's how you get the unit of acceleration as meter per second square. Again, if we talk about rate of change of velocity, we also have to take care of two terms. One is the initial velocity, which is represented by u, and the final velocity, which is represented as v. Now this initial velocity will obviously be zero when the object is in a state of rest, it is not moving, right? So this is the velocity at the very start of the journey of an object, and final velocity, as we all know, is the velocity after this initial velocity, or the velocity that this moving object has acquired after acquiring some initial velocity. So again, mathematically you can write acceleration as rate of change, which is final velocity minus initial velocity upon time. Very simple. Now let us have a look at this very simple numerical. This numerical says that a scooter traveling at 10 meters per second speeds up to 20 meters per second in 4 seconds. So you're given the initial velocity of the scooter as 10 meters per second, and you are given the final velocity of the scooter as 20 meters per second, and this change in velocity basically takes place in 4 seconds. So the time that's given to you is 4 seconds, and you're supposed to find out the acceleration of the scooter. Take a minute. You can write your answer in the comment section as well, and in the meantime let me just give you a very realistic example. You would have seen athletes around you, right? Marathon runners basically. So these marathon runners, they start off slow and then they speed up. So they are not running at a constant speed or a constant velocity. At the start of the race they are very slow, and then suddenly they buckle up, they increase their speed, they increase their velocity, and that is a state where they acquire some kind of acceleration. They undergo a rate of change in their velocity, and that is the reason why they do not run at the same speed throughout the journey. They undergo some kind of acceleration. Another example, let's just say you're running, you're playing around with your friends, and suddenly a dog chases you. So your jolly happy nature of you playing with your friends or mingling here and there will suddenly change to a state of panic. You will start running, So in that process, you're basically increasing your velocity. Vice versa. Let's say you're running here and there, and suddenly you see your dad or your mom, and they tell you, "Putar, ghar aaja." In that process, you slow down, right? You tend to process, अरे ये क्या हुआ, बीच रास्ते में मेरे मम्मी पापा ने मुझे ऐसे कैसे रोक लिया. True, no? So that is a practical application of acceleration in your real life and the ones mentioned previously. So coming to the question, it says find the acceleration of the scooter. You're given the initial velocity, the final velocity, and the time taken. So acceleration, which can be mathematically written as the rate of change of velocity. So let's find out the change of velocity. So the final velocity is 20 meters per second. The initial velocity is 10 meter per second, and the time that's given to you is 4 seconds. So the acceleration is 10, 10 by 4, which is 2.5 meter per second square. Simple, very simple. Let us have a look at this numerical. It says that a train starts from rest and accelerates uniformly at the rate of 5 meter per second square for 5 seconds, and we are supposed to find out the velocity of the train in 5 seconds. Now it's given to you that the train starts from rest. It starts from rest. So the initial velocity of the train, that is u, will be equal to 0 meters per second. You're given that this uniform acceleration of 5 meter per second square takes place for 5 seconds. So you're given time as 5 seconds. You're supposed to find out the final velocity of the train, like the velocity of the train after 5 seconds. So again, acceleration, which is defined as the rate of change of velocity. Now this is the change, that's v minus u, and it's happening in 5 seconds. So t is 5 seconds over here. But now in this question you are given acceleration as 5 meter per second square. So what is not known is the velocity, and the initial velocity is 0 meter per second, and the time over here is 5 seconds. So you get v as, because v minus 0 is v, so you get the value of v as 25 meters per second. So in our previous videos, we've had a discussion on the types of motion. We've also seen a couple of real world examples of those types of motion that we've discussed before. And now we'll try to depict the following types of motion in the form of a graph, basically a pictorial representation of motion. So if we talk about graphs, in the context of this chapter, we'll be learning about position time graphs. Position time graphs basically refer to distance versus time graph or displacement versus time graph. But in general, you can use the word position. So, position time graph, and you can write the position time graph as xt graph if you want to represent it mathematically, because you see a couple of questions where you will see draw an xt graph, so that should not create any confusion. So the symbol for position is x, be it distance or displacement. Some books also use the letter s, but both x and s are fine for position, be it either distance or displacement. And the second type of graph over here that we'll be learning is the velocity time graph. or the VT graph. Now, as the name suggests, one graph basically gives you the variation of position with respect to time, and the other graph basically gives you the variation of velocity with respect to time, right? That is the primary difference between the two graphs. But before we start off with these graphs, let us have some mathematical understanding of variables, because position, velocity, or acceleration, these are basically variables attributed to the motion of an object. So let's have a brief discussion on these variables first, and then we'll look into the various kind of graphs that we'll be exploring under position time graphs and velocity time graphs. So as we all have learnt in mathematics that to draw a graph, a basic graph which has two variables, you need an x-axis and a y-axis. Now on the x-axis you have the independent variable. In this case it is time. Let's just say that we are there in an offline class, and I am standing at one place and I'm interacting with you. I'm standing at one place vis-a-vis a situation where I am roaming here and there in the classroom. Now in both the cases, time is progressing uniformly. Even if I stand at one place and I talk to you, then also time is progressing uniformly. And even if I run here and there and talk to you, then also time is progressing uniformly. So time is independent of my position. Time is not waiting for me. Aha, क्या गहरी बात बोल दी मैंने. Time is not waiting for me. It does not wait for anyone. Right? So that is how time becomes an independent variable. So independent variable. Now if you look at velocity, position, or maybe acceleration, all these variables are affected by time. They are dependent on time. So you plot the dependent variable on the y-axis. So this can have position, velocity, acceleration, and our graph somewhat is like this. When you talk about labeling the axis, so our graph will look like this. Now let us explore both the types of graphs. If I talk about position time graphs, we'll be drawing a position time graphs for bodies at rest, for bodies in a state of uniform motion, and for bodies in non-uniform motion. So we start off with our very first case, at rest. Now we are drawing the position time graph of a body at rest. So you have your position on the y-axis and time on the x-axis. Now at rest, what basically happens is that the position of an object does not change with respect to time. That means if this is x equal to 5 meters, now throughout this interval of time on the x-axis, mind you, this is not the position x, this is the coordinate x. So throughout this entire time interval, the position is not changing. The position is not changing. Like, let's take another example, x equal to 2 meters. the position again is not changing with respect to time. X equal to 10 meters. So if a body is in a state of rest, then the position time graph for that body will be a line parallel to the time axis or the x axis. And this x, again I'm repeating, is not position, it's the coordinate x axis. Now, uniform motion is basically defined as a type of motion where an object covers equal intervals of distance in equal intervals of time. So, let's just say in this case, an object covers 1 meter in 1 second. So, I plot this over here. Here, x is in meters and time is in seconds. Now, after covering 1 meter, it covers another 1 meter in the next second. So that means it basically covers 2 meters in 2 seconds. Then it covers 3 meters in 3 seconds. And then 4 meters in 4 seconds. So you can see that with increase of time by 1 second, the object is covering 1 meter. So if I connect all these points, you get to see a straight line over here. So the position time graph for a body undergoing uniform motion is a straight line graph. Now let us have a look at the third case of non-uniform motion. And here as well we are trying to draw the position time graph. Position on the x-axis and time, position on the y-axis and time on the x-axis, and over here the position does not change uniformly with respect to time. So it can be something like this. So there is a non-uniform increase, then maybe in this interval the object is at rest, and again it increases, but it increases linearly. So if you see the motion of this object in intervals from OA to AB and to BC, the motion of this object is not uniform, because in the interval OA it is increasing non-linearly, right? In between the points A and B, the object is in a state of rest, its position is not changing with respect to time, and beyond B, the position changes linearly. So this kind of a, so here are some position time graphs that I've drawn for you on MS Excel for all the cases, for a body at rest, for a body that is in uniform motion, and for a body that is undergoing non-uniform motion. So you have some live numbers over here that will give you a better feel, and the graph over here is obviously neater than a manually drawn graph. So yeah, starting off with the position time graph for a body at rest, you see that time is increasing uniformly by 1 second, but in this time interval from 0 seconds to 5 seconds, the position remains the same, 4 meters. It is not changing with respect to time. So you can see in the graph over here that the line is it's a blue line which is parallel to the time axis over here, and that depicts the position time graph for a body in a state of rest, as we saw previously on the whiteboard as well. This second graph, which is the position time graph for a body in uniform motion. Now let's look at the numbers and try to analyze the type of motion. Over here again time is increasing uniformly by 1 second, and if we take a look at the position over here, the position also increases uniformly by 4 meters. Like it's 0, then 4, then 8, then 12, then 16. So it's increasing uniformly by 4 meters. So you get a straight line graph over here, and that is the position time graph for a body in uniform motion. Now let us have a look at the position time graph for a body which is in a state of non-uniform motion. So you take a look at the numbers over here. Again, the same exercise. The time over here is varying uniformly by 1 second. The time is not waiting for anyone. The position over here is not changing uniformly with respect to time. At first, like at time equal to 0 seconds, the position of the object is 3 meters. At time equal to 1 second, the position of the object is 8 meters. Then at 2 seconds it's 17 meters. Then at 3 seconds it's 21 meters. So the object covers 5 meters between the time intervals 0 to 1 seconds, then 9 meters between 1 to 2 seconds, then 4 meters between 2 to 3 seconds, then again 9 meters in 3 to 4 seconds, and 37 meters in 4 to 5 seconds. So this is the difference that I'm talking about. See, this is 5 meters, 8 minus 3. Again, 17 minus 8, this is 9 meters. Then 21 minus 17, that's 4 meters. Then 30 minus 21, that's again 9 meters. And then 67 minus 30, that's 37 meters. So this increase, or this change rather, is not uniform. And that is the reason why we got a non-linear graph for an object which is in a state of non-uniform motion. So let's consider a case of obtaining velocity from a position time graph, because we've learned that the rate of change of position, or displacement rather, is defined as velocity. So we've understood how we can obtain velocity numerically from displacement. So let us also have a look at how we can obtain the velocity of an object with the help of a graph. So velocity from a position time graph. Now we all know that for the position time graph, we plot position, or x, the variable x, on the y-axis, and time on the x-axis. So let's take a simple example, x and t. So time is 0, 1, 2, 3, and let this be a case of uniform motion where the position is varying linearly with respect to time. So let's just say that the position is also 0, then this is 3, 6, and 9. So we have some numbers to begin with. This point over here becomes the origin, and this is 1, 2, this is 3, this is 3, this becomes 6, and over here we get 9. So we have our coordinates as 0, 0, 1, 3, as you can see from the table, 2, 6, and 3, 9. So it's a linear graph. It's a linear graph, and You get a straight line graph over here. Now, if you want to find out the velocity from this position time graph, you should be having information about the rate at which the position of this moving object is changing, obviously with respect to time. So I will mark the coordinates over here. Now, how do I obtain the velocity from this position time graph? Let's consider the points 3, 9 and 1, 3, and I basically draw a dotted line from 1 to 3, and I draw another dotted line from this coordinate 3, 9, and you can see that at the points 3, 3, these dotted lines basically tend to meet each other, right? Now, mathematically, velocity is also called as the slope or the inclination of this straight line. So, the rate of change, which is also called as the slope of this straight line or the inclination of this straight line, basically gives you information about velocity. So, we've marked 3 points over here. We have a triangle, and let's label the triangle as A, B, and C. Now, the inclination, which is this angle over here, let's name the angle as alpha. Right? Now, this dotted line is parallel to the x axis. So, this angle will also become alpha because this is a corresponding angle. Now, to find the rate of change, velocity, what I do is I basically take the ratio of AB upon BC. Now, if I want to find out AB, I have to basically do this simple exercise. I have to find out the length of this green line first, and then subtract this sharp red line from the green line, right? So the length of this green line is 9 units, right? So AB over here becomes 9, and I have to subtract this red line from this green line, and this red line is equal to 3 units. So 9 minus 3, that is AB, and I divide this by BC. So if I talk about this entire length from the origin to point B, that is basically equal to 3 units, and I have to subtract this length now. So basically I start from the origin, this entire red line, and I have to subtract this small green part so that I can get the value of BC. So the entire red part was basically equal to 3 units, and this small green part is basically equal to 1 unit. So I get V as 6, that's 9 minus 3, and 3 minus 1 is 2. So I get velocity as 3 units, and assuming that x is in meters and time is in seconds, so my velocity becomes 3 meters per second. So in general, if I have a point over here which has coordinates as t2 comma x2, and I have a point over here as t1 comma x1, I can say that the velocity is equal to x2 minus x1 upon t2 minus t1. Very simple. Now, based on whatever you've understood in this section of the video, I would like you to answer a question, a simple question. I'll draw a position time graph and I have object 1, which is this red object, object 2, which is this green object, object 3, which is this blue object over here, and you have to tell me which of these three objects has the maximum velocity and the minimum velocity. So you have to find object with maximum velocity and object with minimum velocity. So you can share your answers in the comment section, and thank you so much for watching. Thank you for always supporting and encouraging. And till then, take care, stay safe, and happy learning. Bye bye.